My name is Michael Daly. I'm a special projects engineer and I'm working on the reusability project for Electron. So at the moment, recovery is focusing more on the how do we get this thing on a boat and back to the factory. What we're going to be doing in reuse is that back end. So processing it on the boat, what can we do to operationally to clean it, to prevent that corrosion buildup and that lasting damage that will happen over the following weeks due to the salt, as well as contributing to design changes and leading that sort of thing with the vehicle design teams, the propulsion development teams and all that kind of stuff, just to achieve a rocket that we're going to be able to use it a few times, you know. So I'm going to be located on the boat, and once that launch happens, the recovery team that we're going to be working with is going to be looking for where we're going to see a re-entry of the vehicle, and then preparing to go and collect it out of the water. My job there is going to be supporting them initially in those operations to get out of the water, and then I'm going to move into the operations that I've been building up. So that's the operations like desalting, the engines, trying to remove all that bad salt water, and basically just trying to make the rocket survive that experience with the water. We're going to be doing some modifications to the engine as well in terms of design to make them more resilient. We're actually calling it the Engine Resilience Project, trying to build these guys up. So a mixture of these desalting operations once it comes out of the water, as well as these design changes, will hopefully mean that we have to do minimal testing once we get these guys back. So it's going to be saving us a whole lot of money. Looking back at our previous recovery, we have been able to reuse some of those components, which gives a fantastic indication that we're going to be doing even better in this next recovery, especially with our new operations and designs that we've been changing. So we're going to be recovering more of those components, reusing more of those. And we fully intend to be reusing some of our components coming out of that. Once it returns from flight, all of our avionics components particularly, as well as our propulsion components, we have the ability to start testing them again and seeing what they look like post. And then the propulsion side, we're going to be disassembling these engines and seeing what signs of corrosion is in there, if what we've been changing on the engine has worked, and then making a game plan to make it work even better the next time.
And that covers what we can expect from the secondary mission for today's Electron launch and the process as we take our next steps to make Electron the world's first reusable small rocket.
We've spoken a lot about how Electron works, but as you'll know, the whole reason we are here today is to put our customers' satellites in orbit. And not only do we perform that primary task, but at Rocket Lab, an even larger chunk of our business is building satellites themselves and the parts they need to work properly when they're in space. Here's a breakdown of the essential components of a satellite. First, in order to leave the rocket behind, a satellite needs a separation system. One side of the system is attached to the rocket and the other is attached to the satellite itself. A timed separation event will deploy the satellite at the precise moment needed to get the spacecraft in its proper place in the skies. And these separation systems are one of the space systems components Rocket Lab provides small satellites across both our own launches on Electron and for launches on other rockets.
Next, satellites can't perform their intended functions without power. So solar panels charge the batteries on the satellites that keep the sensors running so they can collect their mission data. We provide these too, from individual solar cells that make up a solar panel to multiple solar panels wired in series to create an entire solar array. You've likely seen some of our solar solutions across some of the most important missions in space recently, including the James Webb Space Telescope, NASA's Parker Solar Probe, and the Mars InSight lander.
Now, once in space, when a satellite passes over a ground station and needs to point an antenna at the Earth or wants to point a camera at a specific location, it needs attitude sensors and actuators, and Rocket Lab builds both. Attitude sensors, like the star trackers Rocket Lab makes, determine the orientation of a satellite. They are small star finders that compare what they see in space to star maps to find out where the spacecraft is pointing. Rocket Lab also builds actuators called reaction wheels that are used to correct the satellite's pointing depending on what the star tracker says. Together, they ensure the satellite keeps the solar panels pointed at the sun and the antenna pointed at the Earth.
And last but certainly not least, a satellite's space software keeps the payload connected and communicating with the teams on the ground managing the mission. And that's the gist of what makes a satellite a satellite. Speaking of, let's get back to the mission at hand and see where we are for The Beat Goes On. We are just 2 minutes away from launch now. Electron remains in good health and the Black Sky satellites inside the fairing are good to go. The weather remains green and the path to orbit is looking clear from Launch Complex 1 at T0. Soon we'll hear the call that LOX loading is complete on Electron, telling us that the rocket is fully fueled for launch. Then our launch director, Julia Wembacher, will be counting down the clock from mission control at T-minus 10 seconds.
We're going to hand over now to mission control and we'll be back after liftoff to take you through the launch milestones.
All avionics batteries have switched to internal power. Ground power has been disabled. Vehicle is fully on internal power. FTS is enabled for flight.
LOX load complete, system in recirculation. Anti-geysering system disabled.
Stage 1 and Stage 2 are pressed for flight.
High flow engine purges enabled. Deluge activated.
T-minus 20 seconds and counting. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Beginning pitch over. Stage 1 propulsion is nominal.
All right, T plus 32 seconds and our 35th Electron mission is off the pad and on its way to orbit. The next mission milestone will be max Q, when Electron experiences the most amount of mechanical stress as it heads skyward at the intersection of vehicle speed rising and air density dropping.
Electron is supersonic. Approaching max Q. Past max Q.
There it is from Mission Control. Electron has cleared max Q and is now throttling back up to full noise as it continues onto space.
We are currently travelling at a speed of 2,400 kilometres per hour and at an altitude of 22 kilometres as we approach the next mission milestones. 3 in quick succession this time. First, the 9 3D printed Rutherford engines will throttle down before shutting off completely. This is known as main engine cutoff, or MECO for short. Then we'll have separation of the first and second stages, followed quickly by ignition of the single vacuum-optimised Rutherford engine on Electron's second stage to carry us the rest of the way to orbit.
When Electron's booster is on its way home to Earth, we will try and stick with the Stage 1 live camera feed for as long as we can so we can watch Electron's ocean recovery attempt unfold. But for now, it is back to mission control for those next 3 launch milestones.
Entered burner into deck mode.
MECO confirmed. Stage 2 ignition successful.
Stage 2 guidance nominal.
Right on cue there with MECO stage separation and
successful.
ignition of the Stage 2 Rutherford engine. Next on the checklist is separating the rocket's fairing and jettisoning the nose cone that protects the payloads during flight. This middle of the night launch means it might be too dark to see the separation event on our screen, but keep an eye out anyway as we listen into mission control for the call out.
HVB battery discharge is nominal. Fairing jettison succeeded.
And there's the
Stage 2
confirmation
propulsion
we were
nominal.
waiting for. Electron's fairing has successfully been deployed. Stage 2 is continuing well with its payloads to orbit. The vehicle is currently reaching speeds of more than 8,500 kilometres per hour at an altitude of 135 kilometres.
Stage 2 propulsion holding nominal.
All right, at over 11,000 kilometres an hour and more than 180 kilometres in the air, this first launch from LC1 this year is going fantastic so far after 2 back-to-back launches from LC2 that started 2023 for Electron. That second LC2 mission actually flew just last week, so launching today marks the fastest we have ever turned around 2 missions. Our previous record was 15 days in 2022 between Capstone and a mission for the NRO. Back to the beat that goes on though, and as I said, all looks nominal. You can see there that Stage 2 Rutherford engine is burning bright to orbit.
Stage 2 guidance nominal. 200 seconds remaining.
HVB battery discharge nominal, approaching hot swap in roughly 30 seconds.
So with Electron's second stage now at over
Throttling down.
194 kilometres in the air, the vehicle will be coming up on its next event, the action of swapping the batteries that keep the second stage's Rutherford engine going. As our 3D printed engines are powered by batteries, by this point in the launch sequence, those batteries are getting low on energy. And as you might have caught on your screen there, they have since dropped off because our engine has switched to the other set on board to keep it going. That's why we call it the battery hot swap.
Electron Stage 2 continues on its way to orbit at an altitude of 198 kilometres and a velocity of 17,000, kilometres per hour.
You saw it there for a brief second, but it looks like we have actually lost the video connection to Electron's booster coming back to Earth there. That's not to be unexpected, so don't panic. It's when the stage moves out of range to receive the live camera telemetry. We are still expecting the first stage's main parachute to deploy shortly at about 8 minutes into the mission. And we'll continue to listen into mission control to hear whether that's gone ahead.
Stage 2 performance holding nominal.
Main parachute deployed on recovery.
We have just heard from Mission Control there that the main chute was successful. The Electron is now powering its way down to 158 metres per second ahead of the stage landing in the ocean.
So with a velocity of 26,000 kilometres an hour and an altitude of over 191 kilometres, the final mission milestone for the second stage will be SECO, or second engine cutoff. And that is when the Rutherford engine throttles down before shutting off just ahead of Electron's third stage, what we call the kick stage, separating and carrying on with the mission with Black Sky's payload. And as you just saw there on the screen, we have had that successful shutdown of that second stage. So it's now onward for our third stage to deploy those satellites to orbit.
Black Sky's satellites are heading to a circular orbit today, but at the moment our kick stage is on an elliptical first pass. To get into the required circular orbit, we have a tiny engine on the kick stage called Curie that will course correct the mission by orienting the kick stage on the right trajectory for payload deployment. We won't have live video of this payload deployment for this mission, but we will be back to listen out for those final few calls from Mission Control, along with an animated view of the end of the mission to visualise what is happening up there in low Earth orbit.
Meanwhile, for recovery, the stage 1 splashdown is expected in approximately 8 minutes. We'll come back from our break to watch and discuss while the camera feed is up if we can get it. So stick with us for confirmation of that shortly. We'll see you back here soon.